So Professor Yuan Zhou, you can share the screen and turn on your camera. I'll stop sharing here while I can make introduction. Okay, the first talk of this workshop will be given by Dr. Yuan Zhou, who is an associate professor at Yale Mathematical Science Center of Tsinghua University. 就是清华的邱成桐数学科学中心。Now, before joining Tsinghua, Dr. Zhou was an assistant professor at the University of Illinois Urbana-Champaign and also an assistant professor at Indiana University Bloomington. And his research interests include online learning, decision-making, combinatorial optimization, and their applications to revenue management, and such as dynamic pricing, inventory control, and so on. He's currently served also as an associate editor for operations research letters. So actually, just a remark, every talk here would be 25 minutes, including question and answers. So for the speakers, you can go ahead and at around 20 minutes, 5 minutes towards the end of talk, I will turn on my camera just as a reminder. And for the people in the audience, if you have questions, you can raise your hand. There's a button for you to do so in Teams, or you can write your chat message in the chat box for a question. And I, as a chair, will look into that, and we also have volunteers to help look into this. So without further ado, let's give our mic to Dr. Zhou.
Great. Okay. So can you hear me?
Yes.
Yes. Oh, great.
Very good.
Okay. Thank you, Professor Chen, for the nice introduction, and also want to thank Professor Sun for the opening remarks. So I would like to echo the theme of this workshop that data-driven optimization is very important in this big data area, and it has also been revolutionary to many application fields. So in this presentation, I'm going to talk about a few of our recent works on data-driven revenue management. So in our works, sometimes one needs to make multi-stage decisions that involve multi-stage optimization. And sometimes the data is only partially observable. And to make things even more challenging, sometimes the reward might also not be fully observable. So to address these challenges, it is important to develop new learning techniques to actively and carefully query the data so that our reward optimization goal may be achieved more accurately. Okay, so I'm going to, and also, by the way, this presentation is based on joint works with Barry Chen, David Simchi-Levy, and Yining Wang. And so because of the time constraint, so I'm gonna spend most of the time on introducing the problem models, and I will also briefly talk about the technical challenges and our solutions to these problems. Okay, as an overview, so for operations management and revenue management, so I think there are three very important problems. So one of them is called assortment optimization. That means we want to choose to decide which kinds of items we want to sell. And the other two are also the fundamental problems, and they are also the key in this presentation, are called pricing and inventory control. So given the items we want to sell, so the other two decisions we need to make is at which price we are going to sell them, and how many items we want to keep in the inventory for them to sell. Okay, so in this talk, let's forget about the assortment part. So let's assume that we have already decided. So the single item we are going to sell, and the pricing task is just so involves the trade-off of balancing the revenue and demand. So as very intuitively, you can see that. So the higher the price, the more revenue we have, but also so this would lower the expected demand given this price. And on the other hand, so the inventory management problem also involves another kind of balancing problem. So that is, we need to balance the ordering cost, holding cost, and the out of inventory cost. So you see that the first two costs. So let me turn on my laser pointer. So the first two kind of costs will be smaller when we have like a larger inventory. But if we'll have for a smaller inventory, but then it will increase the out of inventory risk. Okay, so this is the two key problems we are going to consider in today's talk, and we are going to consider them all together. So let us look at the formal decision process we are going to make. So in the first step, so these decision steps, we are going to make it like iteratively, rounds by rounds. So in each round, so the first step, we are going to make inventory decisions. So that means that at the beginning of this round, also we also call them time. So we have a initial inventory level, so we call it xt. And then the decision we are going to make is the so-called order of two level, so which we denote it as yt. So yt is usually should be greater than xt, and then the number of new inventories we introduce will be yt minus xt. So that is very simple. And now the ordering cost would involve two parts. So one part is the so-called fixed cost. So it's the setup cost if we decide to introduce any new inventory. So as long as yt is greater than xt, we have this single fixed cost k. So that would involve some like say the setup cost for arranging transportation and so on. And the other cost, part of the cost is called the variable cost. So this will be linearly grow with the amount of new inventory we are going to introduce. So that will be c times the number of new items we introduce. So that is yt minus xt. Okay, so this is the first step, the inventory decision step. And now in the second step, we are also going to make the pricing decisions, as we say that we are going to consider both inventory and the pricing in this single problem. So now recall that we already have made our order up to level decision yt, and now the pricing decision pt would lead to the realized demand dt. And indeed, so this would be the expected demand given this price pt. However, so the real demand would be so this d0 as a function of pt would be the expected demand given the price pt, and this realized demand dt would be this expectation plus a centered noise beta t. Okay, so unlike the usual, like say many online learning problems such as Modern Bandits, so our noise is here. Noise beta t's distribution is very important. So different distribution might lead to very different optimal decisions. So later in our learning task, it is also important to learn this what the decision what the noise distribution is. Okay, so after making this price pt, so the remaining inventory would be xt plus 1. That is the current inventory level yt minus the realized demand dt. And also the sales revenue would be, so this would be the amount of demand times the price we sell at this time. So also I would like to emphasize that this amount, the remaining inventory, might be a negative number. So meaning that it could be the case that the demand just overwhelms the current inventory level. So in this case, so we can still sell the whole amount of realized demand, but the extra, say the demand beyond the current inventory level will be done in let's say in a backlogging way, and that would involve more cost, which would be shown up in the next slide. So this is called the backlogging model. And also so there is another kind of model which we also consider is called the censored demand model. So this is also a very natural setting where, let's say, so after all the inventory are consumed, then the demand is just gone, even though there could be so many demand because of the limited inventory. So we cannot serve those demand, and even we do not observe those demand. So now we only observe our remaining inventory becomes 0. So this is what we call the censored demand, and it's also what I meant at the very beginning, saying that sometimes the observation is only partial. Okay, so this is the second step of our decision process, and finally, so we will sum up all the costs and the revenues. So we have before we have already had the inventory costs and also the revenues we realize, and finally here we will introduce a cost, so that would involve in the that would depend on the remaining inventory. So if the remaining inventory xt plus 1 is positive, then we have it will incur a holding cost. So that is the cost for keeping this inventory overnight. And also, if let's say in the backlogging model, so if the remaining inventory becomes negative, then so there is a backlogging cost. So even though in the even in the censored demand model, so the lost demand, so the lost demand, which is this part, so in the negative, so would also incur a cost. So this is so-called the loss of goodwill cost. So that would relate to, let's say, the customers who would like to buy the item, but he or she is disappointed because of the out of the order. Okay, so this is a loss of goodwill cost. And also importantly, so this part of the cost would incur, but they are not observable. So this also makes another layer of the challenge, and also mentioned in the beginning of this talk. So we will use the h function to represent both of these costs. That is, h of xt plus 1 is greater, so it's a positive number, non-negative number for in the either case of xt greater than 0 or less than 0. So it is usually 0. So incurring no cost if we exactly consuming all the inventory. So that means xt plus 1 equals to 0. Okay, so all these steps completes my introduction of this decision process at one round, and this will go rounds by rounds. So to summarize, so at each round we have a state t, and then we need to make decisions. Let's say the order up to level and the price, so namely yt and pt. And for the state transition, so in the backlogging model, so we have this just the yt minus dt to be the new state. And in the sensor model, so this yt minus dt is censored to 0 if it becomes negative. And we will be so the immediate reward incurred at each time would be, let's say, so this first part would be the ordering cost, and this would be the revenue part, and finally here is the backlogging or holding cost. It's related to h. So this is a backlogging model. So in the sensor demand model, so we just replace this part by a sensor demand. Okay, so these are two types of problems, and so we will be, so as mentioned, to echo the theme of this talk, so we will be interested in the so-called learning while doing problem. So here, so the problem models, let's say, so the most important models will be the D0, so the expected demand as a function of price, and also the noise distribution. So these are unknown. So we would like to design a learning while doing algorithm to learn all these unknown parameters, and also to optimize our rewards at the same time. Okay, so this is the problem setting, and here are our results. So these two, so the paper number 1, paper number 2 in bold fonts, so this represents our results. So we will discuss like two types of results. So they are differentiated by the very important feature here is whether K, so as a reminder, K is the fixed cost in our ordering, so in our ordering cost, so the setup cost. So if there is a fixed cost, or there is no fixed cost, so this will give the problem very different nature and structures. So if there is a fixed cost, then the problem becomes more like a reinforcement learning, let's say multi-stage decision problem. That is because we tend not to make very frequent inventory replenishments because of this cost. So if we do not have this cost, so then we do not have this type of constraints, and we can just refill our inventory at every time step. So this becomes more like a bandit problem, because at each time step, we might make the same optimal strategy. But if we have a fixed cost, so we will take that into consideration, and we might only, at some time, we make a replenishment, and after a long time, we do not refill our inventory. So that is like a multi-stage decision problem, more like a reinforcement learning problem. Okay, so for the fixed cost problem, so we will consider a generalized linear pricing model. And here, to make things simpler, so we do not consider the censored demand part. So that means that all the demands that we can observe. And in this type, we achieve an optimal of square root t regret. And so this is in comparison with the previous work, where, say, the previous authors, so they do not have a pricing model, so that will be a pure inventory control problem. So in this sense, we would our work like extend and generalize all these previous literatures. Okay, so in the second type of our work, so here the problem becomes simpler because we do not have the fixed cost, but the problem is more challenging here due to the censored demand. And we also have a nonparametric pricing model. And here the problem becomes challenging in two folds. So one thing is because of the censored demand, as I mentioned, so we do not fully observe, we cannot fully observe the model response. And the other thing would be, so because of the joint inventory decision and the pricing problem, then there is no natural concavity or the convexity structure in this problem. And so we can compare with a bunch of previous works here. So most of these works would just forcefully assume such a concavity to achieve meaningful regret. And also some of the previous work, so they either only consider the pricing model, or they only consider the inventory control model without pricing. Okay, so in this sense, we consider the full combination of pricing and the inventory control, but we do not add additional convexity or concavity assumptions to the model. Okay, so this is a summary of our results, and also the problem introduction. And I guess I only have about 10 minutes, so I will briefly talk about the main challenges, technical challenges in these two parts. So for our first part, recall that now it's a multi-stage problem because of the fixed ordering cost. So, but we have a backlogging observation without censored demand. So the H function is V-shaped, you see in this way. And so we have a fixed cost, and we assume a linear demand. So before I said it's a generalized linear demand model, but it's, so for simplicity, let's just look at linear demand, and the GLM model would be an easy extension. And so this will be our immediate reward at each time step. Okay, so this problem seems to be like kind of have a complex structure because of the multiple problem parameters and decisions. So, and it's indeed also a complex but important problem. So in literature, and so there are several important papers. So more than a decade ago, studying this problem in the so-called full information setting. So that is when we know all the problem parameters, and these problems studied the structure of the optimal policy. And they say that in the long run, the optimal policy is so-called a SSP policy. That means the optimal policy is characterized by these parameters S and P. The capital S would be the order up to level. So whenever we would like to make an order up to, so we always order up to level capital S. And the little s controls so tells us when do we want to initiate a reordering. So that is only when the inventory drops below this small s. And this vector P, also a function P, is just a pricing function that maps the current inventory level to PT. Okay, so given these parameters, it's easy to form a policy. And so this previous work say that in the long term, so this is the structure of the optimal policy decision. Okay, so this is a full information solution, and the full information solution is quite easy to computationally easy to figure out by the dynamic programming technique. And so the key is to design this dynamic programming function phi. So it's a function of the states x, and indeed, so we are going to binary search our optimal average revenue R, and parameterized by this R. So we'll look at the reward surplus. So that would be the optimal reward surplus function phi t. And we can easily design a, let's say, a dynamic programming formula here to figure out this reward surplus. And this would help us to decide whether our R is greater than or less than the optimal average reward R star. Okay, and so this is the full information setting. And now let's move to our learning while doing question. So let me briefly first talk about all these previous approaches as I mentioned before. So they would all assume some convexity or concavity structures, and then usually apply the simple explore and exploit or stochastic gradient descent based on these convexity and concavity assumptions. And for us, so we explore a more combined, let's say, learning while doing algorithm, and we would like to divide our t periods into epochs, and each epoch is just very simply saying that it's the time steps from when we do the inventory replenishment to the next time we redo the reordering. So this is called an epoch, and we are only going to update our policy at the end of each epoch. And then for this fixed policy, we would run it for another epoch and to collect the data. And how to make the policy update? So we need first to estimate the demand. So we use the popularly known framework called the upper confidence bounds. So we first do a ridge regression for our linear price demand model, and we compute a confidence interval for this demand model at each price, and then we can compute the upper confidence bound. And we can, it's kind of challenging, but we can still do it, manage to do it to prove that. So using this upper confidence bound for the demand model, so we will compute in the previous slide, so in the full information setting, to compute the optimal to compute the optimal reward in this way. So that optimal reward would also be an upper confidence bound for the real optimal reward. But now the key challenge would be to upper bound that the difference between the UCB of the reward with our realized reward. Okay, so the reason that is a challenge because it's raised because of the multi-stage thing, this multi-stage decision problem. So just to illustrate, let's say if we start from an inventory level S at some time step, let's namely say it's time step 1, and at the first time we do a decision at P, then the due to our estimated model, so then we would incur a, let's say, expected demand of D bar. So this is the UCB. But the realized real demand will be D0. So there will be a difference between the new inventory level, say X2 and X2 prime. So because we say that, so this is the estimation and that they could be kind of close, so we can still say that X2 and X2 prime are kind of close, so that we could still kind of compare these two trajectories between the imaginary trajection and the real trajection. But after this time step, in the second time step of decision, the problem arises because X2 and X2 prime are only, even if they are only a bit different, but this price vector we compute do not guarantee any kind of, let's say, continuous or Lipschitz condition, so that these two price decisions could be very different. And then the realized demand in the real case and in the imaginary case could be very different. And this will lead to the very unbounded difference between the inventory level in the real case and the imaginary world at the time step 3. So now we can no longer compare this imaginary trajectory and the real trajectory, and it's hard for us to bound the difference of the reward. So our solution is to, instead of to talk about the price difference, to bound the price difference, we turn to the stability of our optimal, of our dynamic programming function, and we prove such kind of dynamic programming function has such kind of a stability constraint. Okay, so this will be a variant of the dynamic programming function, but still, so we bound this difference between the real demand and the upper confidence bound of the demand. And so I will skip on some of the technical details, and you see the here key is that we use this stability of the dynamic programming function here. And so this is the way we address this multi-stage decision problems challenge. And there are also some other challenges I didn't mention. So, of course, let's say we need to estimate the whole distribution of the noise distribution. And this would involve several technical challenges we do not see in the usual bandit or, say, reinforcement learning problems. And so this will be the summarize for the first work. And for the second work, so it's the censored demand case. So now it's, we do not have the fixed cost, but now the challenge will be the demand is censored, and we can only partially observe the demand, and we cannot even fully observe the reward because of this this censored demand part. And also in the full information solution, as I mentioned intuitively before, in the long run, the optimal policy will be stationary and myopic, meaning that we only need to commit to a fixed pricing and inventory decision P star and Y star. So this makes the problem more like a bandit problem. So we only need to learn this optimal P star and Y star and repeatedly commit to it at every time step. Okay.
Perhaps you just wrap up maybe some high-level summary.
Okay. Okay.
I appreciate it. Thank you.
Sorry, I thought it's only 20 minutes, but it's 25. Okay. So yeah, so this will be our second problem here, and the key challenge is that because of this kind of censored demand, we do not have either like a zeroth order or first order oracle of our reward. So that means that we cannot observe our reward in any sense of the real value or the gradient. So to do this, we could so our novel technical contribution is that we introduce a pairwise comparison between the decisions. So even we do not observe the real reward, but we can kind of estimate the difference between the decisions, and so that we could learn to decide to figure out the optimal decision. And this, I would like to wrap up our two works. And for future directions, let me just focus on our first question. That is, so we consider the first we consider the challenge of the fixed ordering cost that would lead to the multi-stage decision problem. And we also considered the censored demand. So this is by itself a very challenging problem. So of course, the open question is, if we combine the two challenges, how to address this? So this is kind of unclear in both settings. Okay, so this will be one of the future directions. So the other one, so I will just omit here, but if you are interested, you can talk to me offline. And that's all. Sorry for about the time.
Thank you for the talk. So people in the audience, do you have any question? Yeah, I think Lei Song, my colleague, has some question. Can you maybe just turn on the mic or camera and ask your question directly?
Yeah, sure. Thanks for Professor Zhou's fantastic talk. So my question actually is, why you have some assumption about the demand and so on. So I'm wondering whether we can, or such current approach can solve the general uncertainties that come from the supply or demand, which means that, for instance, there's some fluctuate that come from the leading time, and also there is unknown demand distribution and so on, right? So this is often the case in practice. So do you have some idea on this direction or some existing approach that you can recommend? Thank you.
So if I understand correctly, you are asking about the lead time, or so. And
in general, there's some other the general uncertainties, right? That come from could come from the supply or the demand, right?
Yes, I agree that the lead time is like one major challenge about the uncertainty of the demand, and I think it's so there are multiple works in the revenue management literature, and we also have thought about it a little bit, but I think it's a very very challenging part, and so I do not have any concrete idea I can tell you now, but if you're interested, we can talk about it later.
Sure. Thank you.
Thank you. I also have a quick question, Yuan. So your research for this to work, it's on a single item, right? So
yes.
What if you have multiple items and they have some constraint, like storage constraint, like in a department store, there's only certain storage that you can store those items. Are there some research in this direction already?
Yes. So I'm not aware about the joint pricing and inventory control, but for the single for the pricing itself, or say for assortment itself, and let's say for inventory. So if you just isolate the problem, just talk about these three important problems by themselves. So there are many works, and recently I'm also working with my PhD students at Tsinghua about the inventory control of multiple items.
Good. So it looks like there are some things we can talk more about it. We're also thinking about similar things. Thank you.
Great, thank you.